So welcome to this last session dedicated to technical talks. And the first one is by Professor Jim Phil. He is going to talk about sharpened localization of the trailing point of the Pareto record frontier. Jim, the floor is yours.
Thanks. Good morning, everybody. That is what I'll be talking about. This is joint work with my colleague at Johns Hopkins, Dan Naiman, and my current PhD student named Ao Soon. I think I'll skip over the first two slides of writing and go directly to a picture to tell you about multivariate Pareto records. This is something I've been studying for the last several years. So what you don't see on this picture is observations. Maybe let me go back to the start. Let's just read the top of the slide here. It says, for d greater than or equal to 2 and IID d-dimensional observations, which I'll denote by x super 1, x super 2, and so on, with independent exponential coordinates, I'm going to be studying so-called multivariate Pareto records. Okay, so here's a picture. Imagine in the picture, I drew this before I decided to present things this way. Imagine there are a whole bunch of observations here, right? Both to the southwest of the brown border, okay? What makes the red points here maxima or remaining Pareto records at the current time is the property that these observations have not been dominated in every coordinate. Here, there are only 2 coordinates, not dominated by any other observation. Okay, so as the observations are collected, an observation is said to set a record if it's not dominated by any previous observation. So some observations never are records. Some are records, but get broken by other records, right? And at this particular time in this picture, there are 10 records. They're marked in red. Okay. So if you ask, where would the next observation have to fall in order to be a record, it would have to be to the northeast of this boundary. Okay. So the study of multivariate records really goes back to a 1966 paper by 2 statisticians, a Danish statistician named Barndorf Nielsen, quite prominent in his time, and an American statistician named Milton Sobel. They were studying admissibility in statistics, which, if you know anything about either admissibility or Pareto records, you understand the connection between those two. I won't say any more about that. But they initiated the study of the count of the number of maxima. And if you want to read more about the history, there's a 2005 paper by Zhidong Bai, Luc Devroy, Shenhui Huang, and Tsai that describes the history. In particular, Yuli Baryshnikov, a semi-regular attendee of AofA, claimed in 2000 that there was a central limit theorem for the number of maxima at time n, as you know, a normal approximation as n tends to infinity, and that was first proved in the 2005 paper by the 4 authors I just mentioned. One of the key components to their proof of the central limit theorem was to notice that the observations that the remaining records, or the maxima at time n, are sandwiched between 2 thinly spaced hyperplanes. And Naiman and Soon and I found it interesting to study the sandwiching of the frontier, this border between the record-setting region and non-record-setting region, study it in its own right and say, how close, how narrow can we take the hyperplanes to do this? All right. So I've already explained that the red observations are the remaining records at this particular time n, which must be at least 10. What are the green points? The green points are the minimum points on the frontier, right? Okay, and I'll call the remaining record that has the largest sum of coordinates, I'll call that the leading point, lambda sub n, and I'll call the point on the frontier that has the smallest sum of coordinates the trailing point. Okay, so the trailing point in this case turns out to be this point right here. Before I go on, are there any questions about the setup here? Yeah.
So this example was not grown as 1/1.
This example was what?
Was not grown as 1/1.
Yes, it was. Well, oh, right. No, this is an illustrative figure, right? We obviously could easily do that, but yeah, no, this is just a picture. Where would I expect the trailing point to be? That's exactly what this talk is about. It's a good question, though. So as far as the leading point goes, of course, the current record with the biggest sum of coordinates is also the observation with the biggest sum of coordinates. And that can be studied by classical extreme value theory. And so dating back at least to several decades, we've known, how to study lambda n. Studying the trailing point is more delicate. Okay. So let me set some notation so let me set some notation. First of all, since we're dealing with non-negative coordinates, I could denote the sum of coordinates by the L1 norm. Because in our work, occasionally, not today, but occasionally the sum of coordinates comes up where some of the entries can be negative as well. I've used the notation x sub plus for the sum of x1 through xd, okay? And so this is the hyperplane, x plus equals what it is for the leading point, lambda n, okay? And I'm going to call that value Fn plus. F is for frontier. I refer to this brown path as the frontier of the Pareto frontier. And so the value I'll call F sub n, that's the frontier, F sub n, right? F sub n super plus. F sub n super minus is the sum of coordinates for the trailing point, okay? And it will turn out that we'll be interested in a third hyperplane, namely the sum of coordinates that give the smallest sum of coordinates for any current record. Okay, and so in this case, it's this current record that has the smallest sum of coordinates. And because for practical purposes, that sum will serve as a surrogate for what we were most interested in, this Fn minus, I'll call it Fn hat minus. Now, a little bit about the color coding throughout these slides. Red will always be a cue that I'm talking about something related to current records, R for records for red, right? And green for something called generators. And the reason why these green points are called generators is because in the partially ordered set on, in this case, R2, it's the green points that are the generators of the upset determined by the boundary F sub n, okay? They also turn out to be useful for some random number generation of records, but that's an entirely different story, okay? That's why I'll call them generators. So those are the three processes that I'm going to be interested in: Fn super plus, Fn super minus, and F hat n super minus. Okay, so let me maybe go back to the start again. I'm not going to read through all of this. I've explained much of it just now in pictures, but I do want to say that so Dan Naiman and I wrote a paper in Electronic Journal of Probability in 2000 in which we discussed the frontier, and in particular these processes F plus and F minus. And as I mentioned, F plus is classical, and it's easy to give rather sharp information about F plus. And we did the best we could at the time with F minus. And it was only later that we realized that by using the theory of these generators, together with the first and second moment methods, that we could actually improve on the trailing point results. Okay, so this slide has what we knew then about the trailing point. I won't go through this slide. I'll just say, trust me, if you don't have time or inclination to read this slide, that the results we get using the first and second moment method give significant improvements, significant sharpening of the localization of the trailing point compared to what we could do before. And we invented a certain geometric argument that gave us the best we could do then. We realized first and second moment method do better. And I'll explain for those who are either don't know or rusty what the first and second moment methods are and how we apply them in this situation. That's coming up. Okay. But let me maybe say what our results are. So I have two slides. One is entitled Typical Locations of the Three Hyperplanes. So I'm talking about things like convergence in distribution or convergence in probability. And then I have another slide about almost sure locations. Okay. So typical locations, here's how it goes. Again, this talk is not about FN+, but actually let me maybe go down first to the last line on this slide. So since the observations have IID exponential coordinates, what's sum of coordinates like for a typical observation? The answer is it's gamma distributed with shape parameter D. That is, a typical observation has sum of coordinates on the order of a constant. All three of these hyperplanes start off with, now here's some more notation. I find it useful to use the shorthand notation capital L for natural logarithm and capital L sub k for kth iterate of natural logarithm. It makes for nice short writing. Okay, so typical observations are way down here, right? They're typically have their sum of coordinates of constant order size. For all the records are on the order of log n. In fact, there's a way that you can make mathematical sense out of the notion of a generic maximum or current record X. And then for those, a generic one has distribution that when you subtract off log n, it converges to a standard Gumbel. All right. So typical current records have size about log n plus a constant. The largest one has this sort of behavior. Log n plus dimension minus 1 times log n minus this constant, and then the difference between the left-hand side and this expression on the right-hand side converges to standard Gumbel. All right, so the leading point has sum of coordinates on the order of log n larger than a typical record. What about the small points? What about the minima here? Well, Fn minus, we show in the extended abstract for this conference that Fn minus is log n minus triple log n minus this constant plus big O in probability of the ratio triple log n divided by double log n. Now, I've heard many people, including Robin P. Mantle, another semi-regular participant at AofA, say that mathematics is its most interesting when there are surprises. And I think that we found this result for Fn minus quite surprising for the following reason. Observations have variability on the order of a constant, right? And yet and for Fn plus, you have again variability on the order of a constant. And yet somehow for Fn minus, it turns out that we can pin it down to smaller order than a constant. I don't know why that is. I don't have a good explanation. I mean, I have a proof of this result, but I don't know why it is that Fn, maybe somebody can provide after the talk during the question and comment session, some intuition as to why Fn minus should be determinable so much more accurately than even observations. Okay. As I mentioned, this F hat n minus will play a role in our analysis, and you see that that's the expression I've written here for F hat n minus is almost the same as the expression I've written for Fn minus. It's just that the remainder term is not quite as is a little different from what it is down here. But again, we can determine F hat n minus very accurately. And perhaps the most important thing to notice is this really does serve as a surrogate for this, because the difference between these two, f hat n minus and fn minus, is quite small, right? Little o of 1 in probability, or big O in probability of triple log n divided by double log n. By the way, the reason why these two remainder terms are different is because it's, as you'll see, it's easier to study f hat n minus than it is to study fn minus. If I had to guess, I would guess that the actual order of this remainder term is the same as what it is up here, but the best we can prove is this.
So excuse me.
Yes.
Guess on the size of the difference between these two. I mean, here it's the
Between-
scope by the error terms. But you know anything better?
Well, as I said, I believe that the correct order is this for both of them. Now, if you ask for even finer information, what's the difference between those two? I don't know. And I'll explain as I go why fn minus is more difficult to handle than f hat n minus, right? So in particular, the results that we get for fn minus are determined by getting results for fn hat minus and then making a comparison, right? The simple comparison that this green hyperplane lies to the southwest of this solid red hyperplane. And by the way, apologies to colorblind people in the audience. At least I did put, so, okay, when I've been talking about red, it's dashed here and solid here, and green is dotted here, right? So sorry if you can't perceive the difference between red and green. What about almost sure behavior? As I said, this talk is mainly about fn minus, but it's worth mentioning this rather interesting behavior of fn plus, which was established in the 2020 paper by Naiman and myself. Namely, that there isn't a limit for fn plus minus log n over log n, isn't an almost sure limit. The almost sure lim inf is d minus 1. The almost sure lim sup is d. And in fact, all points in the closed interval from d minus 1 to d are limit points of the sequence, almost surely. So that's sort of interesting. But I will be concentrating on the behavior of fn minus and f hat n minus. We actually have sharper results than what I've written here. They're listed on the first page. I'm not going to go back to that. In other words, I can say more about what the big O of 1 term is here, but I don't think it's worth going back for that. It is worth maybe noting that in one direction, that is for I forget, either lower or upper bound on these things, we can only get the results for d greater than or equal to 3. We can't do better than what we did previously. That might, maybe let me go back to that first slide. That might not be too surprising when you see that what we could do for d greater than or equal to 3 in terms of lim sup behavior has an expression minus the log of d minus 2 in it. Well, that obviously runs into trouble when d equals 2, right? But the sort of problem is that the bounds we get on various probabilities aren't good enough for even a mildly sophisticated use of the first Borel-Cantelli lemma to get us what we want in that case. So we really don't know about the behavior, the almost sure behavior of fn minus when d is equal to 2. That's still open. But as far as the typical behavior, and let me concentrate on this for the talk. In terms of the typical behavior, there's no restriction here. D could be any value, at least 2. D equals 1, of course, is boring, right? There's always, if you have a continuous distribution, there's always exactly one current record at any, right? And it's well known how that behaves. Okay, you may be misled by the pictures that I've shown so far into thinking, oh, this connection between current records and or remaining records and generators, the geometry is quite simple. Well, that's true for d equals 2, right? But here's a picture for d equals 3. Mostly I've kept the color coding to be green for generators and red for remaining records. Here it's still the case that red is remaining records, but I put the generators in 3 different colors corresponding to their what could be called the dimension of the generators. But at any rate, you see from the picture that the geometry is not as simple in dimensions 3 and higher. In dimensions 2 and 3, the number of generators is a deterministic function of the number of remaining records. In dimensions 4 and higher, that's not true. All right. So how do we prove the results about Fn minus and F hat n minus? We do it by switching focus from where the leading point and trailing, sorry, I should just say where the trailing point is located to counts. All right, so we'll let rho sub n of B denote the number of remaining records at epoch n that have sum of coordinates less than or equal to B. And similarly, gamma sub n of B will be the number of generators G at epoch n with sum of coordinates less than or equal to B. And then the idea is that for interesting, suitably chosen boundaries, Bn, what we want to do is obtain asymptotically precise information about the mean and variance of rho n of Bn and the mean and variance of, and the mean of gamma n of Bn. I would also maybe jump down to this remark. I would also be interested in the variance of gamma n of Bn, but that seems to be quite a bit more complicated to study than the variance of rho n of Bn, which is why we've used rho n as a substitute as a surrogate for gamma n. Okay, to get even the mean of gamma n of Bn, we needed to review and then extend the theory of generators that was developed in other unpublished work that Dan and I did. Any questions or comments here? Yeah.
Every time you say location, it's just the sum of coordinates.
Yeah, sum of coordinates. That's an excellent question. You can ask not only what is the sum of coordinates of this trailing point tau n, but where is it located? That we have no current way of handling. That is, you would guess, I think, that it would be uniformly distributed in the hyperplane, but because we can't even precisely, not totally precisely pin down where the hyperplane is, we're not able to say anything about the location within the hyperplane. That's an excellent question. Okay, so yeah, that was the previous slide. Now this one. So I think probably most, maybe all people in the audience are familiar with the first and second moment method, but they're methods for dealing with random variables that are non-negative, usually counts, right? So the first moment method is just an application of Markov's inequality. So the idea is, if we can compute or bound the expected value of rho n of Bn, and if that's near 0, well, then rho n of Bn will be 0 with probability near 1. Okay, but saying that there are no remaining records with sum of coordinates smaller than Bn is the same as saying that the quantity I called F hat n minus is bigger than Bn. So that'll happen with the same high probability. And the first moment method can be applied in just the same way to gamma n Bn and Fn minus, okay? And then, of course, the second moment method involves an application of Chebyshev's inequality. So very elementary ideas here, right? If the expected number of remaining records with sum of coordinates less than or equal to Bn is large, and the standard deviation is of relatively small size, then rho n of Bn will be positive with probability near 1. That is, Fn hat minus will be less than Bn with the same high probability. And now here's how we use Fn hat n minus as a surrogate for Fn minus. Fn minus, the green hyperplane, right, location is smaller than F hat n minus, so then you'll have Fn minus less than Bn with at least the same high probability. All right, so the question reduces to computing two means and a variance. And you might think, oh, you know, is this research level mathematics to compute means and variances? Turns out it's highly non-trivial to get even asymptotics for these means and variances. All right, so so I said for interesting boundaries, we would have to estimate the mean and variance. What are the interesting boundaries? Well, for all of the work about F hat minus and F minus, it's sufficient to consider boundaries of this form: log n minus triple log n minus log of a sequence Cn that's strictly positive and theta, big theta of 1. And I'm going to assume that from now on. There aren't too many more slides left, but in the ones that are, you'll you'll see this notation beta n, it's useful shorthand for this, n e to the minus bn. If you plug in what bn is up here, you get this is cn log n. Since cn is theta of 1, this is theta of log n. And you'll also see e to the minus beta n, which that's beta n, of course, is just log n to the minus cn, and log beta n, which is just triple log n plus log cn. So that's triple log n plus theta of 1. And the asymptotics I'm doing are always with the for fixed dimension as n tends to infinity. You could always ask questions like the one that was asked at the end of the last talk. Like what happens if you allow dimension to grow with n? That would be interesting, and we haven't studied that at all. Okay, so in the little bit of time I have left, let's look at some highlights for the tasks at hand to obtain asymptotically precise information about the mean and variance of rho n of bn and the mean of gamma n of bn. Okay, so for rho n of bn, we're guided in part by the corresponding calculations for the number of maxima or current or remaining records at time n with no restriction about the size. So I'll call that, naturally enough, rho sub n of infinity, right? And so this is the 2005 paper I mentioned before. You notice the title is Maxima in Hypercubes, and you think, what does that have to do with exponential coordinates? Well, obviously, if you're just interested, as they were, in the counts of the number of records, it doesn't matter whether you take the distribution of the coordinates to be exponential or uniform or anything else that's continuous, right? And if you take the coordinates each to be uniformly distributed on 0 to 1, you're just sampling uniformly from a hypercube. So that's why that has the title Maxima in Hypercubes. For generators, for gamma n of bn, we're guided in part by the corresponding calculations for gamma n without restrictions on the sum of coordinates found in earlier work by Dan Naiman and myself. Okay, this may be the last slide I have time to show. I might have a little more time, but we'll see. So expected value of rho n of bn. So how does it turn out? Let me skip for the moment what's written up here. Go down to the lemma. What is the mean of rho n of bn? The claim is it's given by this, or equivalently this, asymptotic expansion. And a natural first reaction in looking at this is, do you really need a full asymptotic expansion? Couldn't you just give the lead term and be satisfied with that? After all, for the first moment method, we just need an upper bound on the mean. The answer to that is yes. For the first moment method, we could get by with just the lead order asymptotics. However, it turns out that in doing the variance calculation, we need to know much more precise information about the mean than the lead order term would give. So this is what we get. Here it involves these integrals that are sort of like incomplete gamma functions, except instead of being z to a power, it's log z to a power, right? I'll make this the last slide, and don't worry, Conrado, I'll finish quickly. Let me just show you how you would start the proof for expected value of rho n and bn. And then let me say that the calculation of the variance, the asymptotic variance calculation, is much more technically involved and complicated and so on, right? So what about for the mean? Well, there you can write down easily what the exact expression is for the mean, right? This is the density for an observation, and for an observation to be a record, all the other records have to fail to dominate it, right? So that it's obviously this. And now here's the nice consequence of the density only depending on the sum of the coordinates. You can transform this multivariate integral into a univariate integral. And now all you have to do is deal with this univariate integral. In particular, you can upper and lower bound this factor using a pair of inequalities that appeared in a 2001 paper by these authors, elementary inequality, right? And the last comment I'll make is this, the remark: the treatment of the expected number of generators at time n with sum of coordinates less than or equal to bn is similar, but on the negative side, obtaining an exact expression requires a characterization of generators, which is of extremely interesting story in and of itself. I didn't have any time for that in this talk. But on the positive side, unlike where here, because I was then later going to go back to, I was later going to go on to study variances. We needed a complete asymptotic expansion for the mean. Since we're only using the generator's results for the first moment method, we only need an asymptotic upper bound. So that's what we got. All right, that's all I have to say. Thanks.
I wanted to make sure that there's time at least for one question.
Yeah, sorry to go a little over there.
Any?
Thanks. Yeah, thanks for the talk. Could you go back to your original picture with the red and blue, red and green ones? I guess any of them really.
This one?
No, the two-dimensional one.
Okay.
Yeah. So saying about, like you were saying, you were surprised that tau n had this order one. Sorry, the typical one had
Okay,
little
okay,
over one behavior. Yeah.
Yeah.
Wouldn't you expect once you have a large number of records, like once you have a large number of samples, these red and green points will be very close to each other, like because there'll be loads of
Sure.
loads of records.
Yeah.
So then, if you the furthest away red one, you take one and it has gumbel fluctuations because if it were a bit further away, that would make the maximum further away. So this is why you need order one fluctuations. But if you take the closest one, the tau n, and make that closer,
Mhm.
it doesn't, like, it goes inside the body.
I see.
Yeah.
So this is intuition as to
Yeah,
why
but this-
it might be that tau n minus is determined, so, or tau n
Yeah,
is
because
determined,
like you move it
Ridiculous.
and it stops being tau n, a different one
Yeah.
becomes tau n. Whereas when you move lambda n further away, it keeps being lambda n.
Yeah.
Would
Right,
this-
I imagine that's true, that if we made a movie of the records, I think it would be the case, right, that you'd see big leaps in lambda n
Yeah,
and then
yeah.
tau n just sort of gradually moves forward. right?
Yeah.
Thanks.
Does that seem?
While he's making his way back, I will tell something to Svante that I promised I would say in this talk and didn't get to. So the variance and the mean turn out to be asymptotically equivalent for rho n of Bn. That strongly suggests a Poisson approximation for the distribution of rho n of Bn. And we tried using the Poisson approximation book for ideas. We tried calculating moments, but even calculating third moment in dimension 2 seems beyond our reach. That's surprising, maybe.
Okay, so here's something else that probably is beyond our reach. So I was thinking, you were talking about the extreme ones, the high.
Yes.
If you try to fix your 45 degrees stuff, can you find some kind of functional limit theorem for the phase of?
Oh, yeah.
There is no functional limit theorem in use of that.
That's on the research agenda. I consider this sort of a microscopic look at the frontier, right? It would be super interesting, I think, to characterize the shape of the frontier on a finer level than just saying it's squeezed between two hyperplanes. Yeah, I think that would be really interesting. I don't know anything currently. Yeah.
So if you consider the generator, do they form the frontier, the Pareto records in the second level? Like, do we move the Pareto?
Oh, yeah. No, that's another super interesting question. And that has been studied to some extent in past literature, right? So Conrado was asking, what happens if you say, all right, let's go back to this original picture. Imagine that there are blue points in the Southwest here that were points that are no longer records, right? But now we do away with all the red points and now say, now we can look at the second level of maxima, right? And where do they lie and what's their behavior, how many are there and so on. And yeah, so I think that Yeah, Shenhui, so do you have like, for example, like mean variance and central limit theorem for the second level? No? Okay, but I think it is mentioned often in the admissibility literature and in the sort of economics literature in dealing with Pareto records, right? So,
Thanks again.